Begin. This first one is going to talk about water. Okay? Now, there's a graph, it should be in the book. There's a graph. Why don't you take out your books? Why don't you take out your books? And I'm on page 511. Okay, I'll make a rough graph here. Okay, this is going to be density. What page? Can you remember that the video was on, so you sound like a bunch of farm animals being taken out for milking? Can we have some semblance of order here, please? Thank you. Excellent. Yes. 511, yes. All right, and it goes like 0.99, it goes like, so how does it go? It goes, somebody read it off to me, 0.9980. Yes, that's really a relevant question considering I'm in the middle of a problem. 9985. 9990.
Yes. Yeah. 9995.
9995. And then 1. Okay. And then it goes something like this ish. Right? Where the significant point is, this is 0, 4, this is 0, 4, 8, right? 4, 8, 12, etc. I don't really care what that is. This is at 4 degrees Celsius. At 4 degrees Celsius, water is most dense, correct? So that sounds like an easy concept, correct? Almost really not a concept, but a definition, yes? But this is what's complicated. This is what's complicated. What has to happen and why for a lake, a big lake? We're talking about like Lake Tahoe, which is roundish and it's about 500 meters deep, okay? What has to happen for that enormous body of water to freeze? Or any body of water, going from a puddle to a giant body of water such as Lake Tahoe, okay? So, here's my that's my lake. All right, it's a cross section of the lake. Okay, now, let's say it's 20 degrees Celsius. The whole lake is 20 degrees Celsius. Okay, the whole lake. Okay? Now, what's going to happen when it gets down to 19? We'll use our little scratch pad. This will be our little scratch pad here. 19. What happens when this water here goes to 19? Like the temperature's dropping. Dropping temp. Okay, what happens? So it goes from 20 to 19. What's going to happen to that 19 degree water? Is the 19 degree water more dense or less dense than 20 degree water?
More dense.
It's more dense, correct. So it's going to drop to the bottom, right? And then all of that water that's 19 degrees will keep dropping until what happens? Until the whole lake is 19 degrees, right? Right? And then, so now the whole lake is 19 degrees. Now, let's jump ahead. What happens when it gets to 6 degrees Celsius? What's going to happen? It'll same thing, and the whole lake will get to 6 degrees Celsius, correct? Yes or no?
Yes.
Okay, now. So what happens when water gets to 4 degrees Celsius?
It gets the most dense.
It gets the most dense, and everything has to fall, right? To get more dense, right? Okay? You get it? Because what happens if there's some water in here that's 5 degrees Celsius? It'll rise to the top. So that 5 degrees Celsius water has to cool off to 4 degrees Celsius, correct? Okay? So this is key. I don't know why this sounds all of a sudden so easy. Maybe you guys are like easier with this, but so what happens when water gets to 3 degrees Celsius?
Everything else will keep rotating.
No, well, all right, keep that thought, but all right, is it frozen at 4 degrees Celsius? No.
Yeah, it wouldn't be roasted because 4 is the most dense.
Well, what happens when water is at 3 degrees Celsius? Will it sink?
It won't sink below the 4 degrees.
It'll float on top of the 4 degrees, right? You see? The temperature, the volume, the density decreases. Does it say volume or density? Yeah, the density decreases less than between 0 and 4. So what's going to happen to this layer? Now this layer can go from 4 to 3 to 2 to 1 to 0.
So the top three.
Why does it not get denser?
Why doesn't it get denser? That's the nature of water.
So it doesn't get denser in another 4 degrees.
No. It gets less dense below 4 degrees. It gets less dense. Water is most dense at 4 degrees
Oh, why?
because it has to do with hydrogen bonding. Look at a snow crystal. The snow crystal will form this nice crystal based on the hydrogen bonding and the tetrahedral type of hydrogen bonding that goes on inside. You have water, right? You have, these are two chemical bonds, and then you have two pen. Then you have two chemical bonds here, are the two markers, and then perpendicular to those, that plane, you have these two that are physical bonds. But look what happens when they lock into place in the water crystal. What happens? You have these two bonds that are locked in because they're chemical, and these two bonds that are still locked in, but they're physical, but they're still locked in. You have to think the orientation. Yes? It's not a true crystal where you have all of these different types of chemical bonds. These are there just because they're hydrogen bonding. So you're changing the orientation of the water. Clear? And what are you creating? You're creating this tetrahedral type structure. Well, what has a tetrahedral type structure? When you think of a precious gem that has tetrahedral structure, what is it? Diamonds, which is carbon. sp3 hybridization, where you have those 4 equal bonds, and that forms the that's why ice is so beautiful. Anybody ever seen ice sculptures? Utterly gorgeous, utterly gorgeous, utterly gorgeous. They look like diamonds, really do. You have ice in your iced tea or in your soda or whatever, and it's just, ice is pretty. You know, the slang for diamonds is ice, you know.
So are diamonds pure carbon?
Diamonds are pure carbon, with some obvious imperfections in there, but diamond is carbon and arranged in a tetrahedral structure. So you have things starting to lock into place, Will, below 4 degrees Celsius. And you have this structure that kind of expands because it's forming this liquid crystal, for lack of better words. I find it fascinating. You're asking me, but you ask the question as if I know the perfect answer, and I really don't. I mean, it's really cool stuff. Yes?
Well, how come diamonds are like crystal-like, but you know how lead has carbon in it?
Lead is lead.
Wait, graphite, yeah.
Graphite is not lead. They call it
pencil lead. It has like carbon.
no.
Yeah, why is pencil graphite?
They call it pencil lead, but they don't really mean that. It's like a slang because look it up. Look up what is the origin of the lead pencil. Look up lead pencils.
It used to be lead, and people found out that people were getting lead poisoning, so
I'm not quite sure that's the reason, but it could be. I don't know. That's what we're going to look up, but that's a very good point, Will. I mean, lead is pretty toxic stuff, and people used to use it as a sweetener a couple thousand years ago. Kind of weird, you know? Yeah, they used to, like, yuck. But no, a lead pencil is actually graphite. It's different. It cleaves. It's not like the same kind of crystal that diamond is. I don't really want to go into it, but it has to do with whatever. Okay, so that's it. So water is most dense at 4 degrees Celsius. Simple. Read that, be able to read that graph. And the reason Lake Tahoe never freezes is, do you see how the entire lake has to be 4 degrees? The entire lake. Now, what is the deepest lake in the world is like Lake Baikal in southern Siberia, north of the capital of Mongolia, which is Ulaanbaatar. It's approximately, maybe look up the depth of Lake Baikal, Baikal, something like that. Look that up, somebody. I think it's a mile deep. I think it's 1,600 meters. I used to have Lake Baikal water. A student brought me in some Lake Baikal water. It's really cool. I kept it in my closet for years.
Depth?
What's the depth of Lake Baikal?
1,614 meters.
All right, so a mile deep. Okay. That lake freezes. So you can imagine what's the temperature at the bottom of Lake Baikal? Does anybody need to look that up or?
Negative
4.
4 degrees Celsius.
Negative
Yeah.
zero.
Yeah. What is on January 3rd, 1884, what was the depth of the water at the bottom of Lake Superior?
What was the depth of the water?
What was sorry, did I say that really?
Yes.
Okay, let me rephrase that.
What was the
All right, so much for my humor. Okay, on January 23rd, 1884, at 4:30 in the morning, what was the temperature of the water at the bottom of Lake Superior? 4 degrees Celsius, very good. Exactly. Now it has to be a big lake because it can't freeze solid, but if it freezes solid, what happens to the fishies? They freeze and they...
But when the lake freezes, only like the top.
Yeah, the top, whatever, foot, 2 feet, 3, whatever, however deep it is. Do you know how they used to get, before refrigeration, you know how they used to...
They chop the ice in them.
Yeah,
Ice box.
that was big. That was enormous. That was an enormous industry. You had a lake in your backyard. You harvested the ice. Really. You had people with saws come in and, hand saws, and you sawed it. It was like a neighborhood thing, and you put these giant slabs of ice. You bricked them up in a barn. You put sawdust on them and whatever to insulate them, and then you carted them by horse to the train. And then the train took them down to Florida or wherever for the fancy hotels, or took them overseas to like Cuba or something, and that's how they kept their gin and tonics cold. I mean, it was for wealthy people. My mother remembers the years before home refrigeration, where you had refrigeration in the cities. You had air conditioning in the cities before you had them in the home. Where did people go to enjoy an evening out in the middle of the summer, where it was like in New York City or Washington D.C., where it's like hell. It's like 110 degrees. It's humid. It's gross.
Is it the ice cube bar thing?
Where did they go for a night out?
Cafe, the bar.
Oftentimes the bars weren't air conditioned. Where was the big place for entertainment that was oftentimes hotels? Yes, but where was the big place where you really went? The movie theater. Yeah, you went to the movie theater. Yeah. Do you ever see? There's a new movie out. I don't know how old it is. Public Enemy.
Yes.
That John Dillinger, he went with his who was the girlfriend of John Dillinger? A little history, American history.
The actress that played it.
No, what was her name? Well, you got to come up with a name, girl. I mean, you got look it up, man. I mean, this is like a famous name in American history. What they do? They went out to the movie theater, and America was really the first country with, the movie theaters were ice cold, and then they started to pop up in all the capital cities in Europe and things like that, and that was the place to go. And then you had hotels that were air conditioned, at least the lobbies were. I've been to hotels very recently that weren't air conditioned, right? Yeah, and what was that place? Kathmandu or?
Billy Fresh
In the bud.
Where was the place we went? That place that we went, that was at UNESCO City? What was it?
The last night of
The
it?
back and forth.
Yeah, back and forth.
No, it wasn't. That wasn't the last night, was it?
That was, yeah, that was the really ancient place.
But didn't we go to Kathmandu?
That was the first thing.
No, I know why.
That's the one that you did, that you like did not want to be in the room with.
Excuse me. Let's not put this on film. I just, Mr. Darcy's a little crazy, but let's not advertise that to the entire world. Okay.
So last night, we stayed at Bakapur and then went to Tamil the next day. And we left.
We stayed at Tamil, or we went to visit Tamil?
We visited Tamil after we stayed the night at Bakapur.
And how do you say the name?
Bakapur.
Bakapur. Is that right? Bakapur.
Well, we only have enough police people here, so.
Yeah.
Neve, we need a, you're the linguist here. You're the artsy linguist type person. You have an answer for us? What was it? No? Oh, that's all right. It's all right. Bakampur, Bakalanpur. Baktapur. Is that it? Yeah, I knew you'd have it. I knew Baktapur. That's right. That's what it is. No, but she said it differently. It sounded familiar then when she said it. Not that the whole world really cares about our trip to Nepal. Okay, that's it. Water. Clear? We're done. Okay?
Oh, clear, water, clear. I got it.